Hello friends, welcome to our next lecture on the Rankine cycle, in which we are going to study the regenerative cycle, ideal regenerative cycle. In the last lecture we have seen the use of mean temperature of heat addition. As we increase the mean temperature of heat additions, the efficiency of a Rankine cycle increases. Mean temperature of heat additions, its meaning is to add the heat at a higher and higher temperature so that efficiency of Rankine cycle increases. If you see the specific heat of water, which is about 4.187, and specific heat of vapor, which is about 2.1 kilojoule per kg Kelvin. So for raising the temperature of water, 1 kg water, by 1 degree Celsius, about 4000 joule energy is required, and for the steam only 2000 joule heat is required for raising the temperature by 1 degree Celsius. Means it is easy to raise the temperature, not easy means it is economical to increase the temperature of a steam as compared to water. Water takes more amount of heat to raise its temperature. Therefore, it is preferred to add more heat at a higher temperature. Okay, and similar concept is used in the reheat Rankine cycle. Ideal regenerative cycle. How it is used, that we will see. If you see the working here, that is, one is the inlet to this turbine. High pressure, high temperature steam enters to the turbine. Then at point 2 dash, somewhere here, 2 dash, the steam is leaving the turbine. But during this process, during this expansion process, there is one more process is happening, that is a raising of temperature of a water. Okay, so how this turbine act as a heat exchanger, reversible heat exchanger with 100% efficiency. This turbine act as a ideal heat exchanger which is having 100% efficiency, no losses. Okay. Okay, then how the temperature of water is increased from 4 to 4 dash. So if you see here on the TS diagram, 4 and 4 dash, this is a liquid water, or the phase of working substance is a liquid during 4 to 4 dash. Okay, and at 4 dash it is a saturated liquid or water. At 4 dash it is saturated liquid or water. So this process takes more amount of heat, 4 to 4 dash, and that heat is absorbed by this water from this steam which is coming into the turbine at state 1 and leaving at state 2 dash. Means this, in one case there is a heat transfer from steam to the water, and water will increase its temperature from T4 to T4 dash. And for increasing this temperature from T4 to T4 dash, the temperature of steam reduces from 1 to 5. Okay, and here it is a 100% heat exchanger. And what is the effect of this heat transfer? Just we have discussed, more amount of heat is required to raise the water temperature, and to reduce that heat is taken from the steam. And as it is a reversible heat exchanger, we can call change in entropy of water is equal to change in entropy of the steam. That is, SB minus SA is equal to SD minus SC. If we equate this, we are getting change in entropy of water is equal to change in entropy of the steam. Then you can substitute water entropy is S4 dash here, S4 dash minus minus S4. Okay, this is a change in entropy of the water. Similarly, change in entropy of the steam is S1 minus S5. This is a S1 and here it is the S5. By rearranging the term, you can take this 5 to the left hand side and S4 dash to the right hand side. Okay, and then S5 is nothing but 5 and 2 dash lies on the same line. We can replace S5 as a S2 dash, and right hand side it is a S1 minus S4 dash. This is mark this as equation 1. This is equation 1. S2 dash minus S4 is equal to S1 minus S4 dash. Now if you calculate the heat supplied, now heat is supplied during 4 dash to 1 process. So by using this formula, dq is equal to TdS and integrate from process 4 dash to 1, we are getting heat supplied is T1 S1 minus S4 dash. Similarly, heat is rejected during 2 dash process to 3. During this process, heat is rejected. So QR is T2 S2 dash minus S3, which is T2 S2 dash minus S4. S2 dash minus S4. Because S2 dash and S3 and S4 lies on the same vertical line, so we can replace S3 as a S4. So this is a QR. Then efficiency of a Rankine cycle is 1 minus QR upon QA. When you substitute this QR and QA in terms of this entropy, we can get this equation. As from equation 1, S2 dash minus S4 is equal to S1 minus S4 dash. It will get cancelled. Then efficiency of Rankine cycle is equal to 1 minus T2 upon T1. This is the efficiency of a Carnot cycle. Therefore, for ideal regenerative cycle, you will get the efficiency of a Rankine cycle which is equal to efficiency of a Carnot cycle. So ideal regenerative cycle gives the highest efficiency in all the Rankine cycle. But it has some limitations. Which are the limitations? You cannot manufacture the turbine which will be act as a 100% efficient heat exchanger. That is one thing. Another thing, if it is not an ideal regenerative cycle, then at point 2 we will have dryness fraction x2, but because of this ideal regenerative cycle, at the exit of the turbine we are getting dryness fraction x2 dash which is less than x2, means dryness fractions decreases during this process. Okay, so 3 limitations are there. 100% efficient heat exchanger is not possible, dryness fractions decreases, and third, manufacturing limitations of this turbine which will be act as a heat exchanger. So in the next lecture we will see how to overcome these 3 limitations, and that cycle we call it as a practical regenerative cycle. Thank you.